Hello, I am Omid from Dynamical System Lab of Temple University, and I'm going to talk about modeling of lithium-ion batteries for real-time analysis and control, a data-driven approach. Here in the outline, at first, we have the motivation, then we define the problem, and then we will find the sparse data-driven model for lithium-ion batteries, and finally, we have the result and conclusion. So batteries are ubiquitous in everyday applications such as electric vehicles or your cell phones and laptops, and lithium-ion batteries are one of the most preferred battery types due to their high energy and power density. Therefore, the electrochemical behavior of them are important for us to improve their performance and their reliability and their safety. However, the electrochemical behavior of them or their physics-based model require many parameters that several are not available, like the thickness of the anode, separator, cathode, or the diffusivity coefficients. So parameters are costly to calculate, and parameters are only applicable to the specific battery and system. So it only predicts the model phenomena, and they are computationally expensive with added complexity. And machine learning methods like neural networks can estimate the input-output response of the battery, but it often lacks the interpretability. So our approach is using a nonlinear reduced order models, which is based on the measurable input and output data. So we are going to use a sparse identification of nonlinear dynamic with control or SYNDC, which is interpretable and control-oriented data-driven model, and it's suitable for real-time analysis. So our goal here is to find the model for the system. So in SYNDC, we use the fact that most physical systems have only few relevant terms that define the dynamics. So F can be considered as a function of linear and nonlinear terms of the input and state. So we can define the theta as a library of potential terms, which can be polynomial and sinusoidal. And by defining a sparse vector of coefficient Kc, we can say that x dot would be equals to theta times Kc. Even here in the figure, it shows that, for example, we can say that we are going to find the active terms in the dynamics of the system. In the figure, only terms of the x and u square plays on the role, and other parameters in the Kc would be equals to 0. So for identifying a sparse vector of coefficient Kc, we will solve it as a regularization problem, and lambda is a regularization parameter which balance between the complexity and accuracy of the system. So if you consider p equals to 1, then we have a norm 1 which results in least absolute shrinkage and selection operator or lasso, and lasso works well for uncorrelated features. If we consider p equals 2, then we have a L2 norm that results in ridge regression, and it works for both correlated and uncorrelated feature. And in this sparsity promoting problem, which is common that the data are correlated, so probably ridge has a better result. And in order to promote the sparsity, we use the sequentially thresholded ridge regression, ST ridge, to achieve the reduced order model. So we define a tolerance, and if our parameter Kc is less than our tolerance, we consider it as 0. And we will do it for the lasso also, and we call that approach ST lasso. So here in the graph, after we defining the library of potential terms, we try to find the Kc based on the ST ridge or ST lasso. And if our parameter is less than our tolerance, we consider it equals to 0. And if it's larger than our tolerance, we do this loop again until non-zero coefficients of Kc converge. So for tuning the threshold parameters lambda and tolerance, mean square error approach achieves the best fit. However, it doesn't consider the sparsity of the systems. But our goal is to balance between the accuracy and complexity of the system, because we want the sparse model that is generalized also. Therefore, we are going to use the ACC information criterion or AIC inspired loss function, which is shown in the box. As you can see, K is the number of non-zero coefficient in Kc. So it considers the complexity of the system, and by increasing the number of K, which means that our system is more sparse. It's less sparse. So for a sparse identification of lithium-ion batteries, we use the enhanced single particle model with electrolyte or enhanced PME to generating the input and output data of the battery. And then we consider two libraries from measurable data. For the model 1, we consider voltage and current. And for model 2, we consider voltage, current, and state of charge or SOC. And when the battery goes through the charge or discharge, the SOC of the batteries would change. So for model 1, voltage is the state and current is the input. So V dot would be the function of the V and I, and then we can define a library of potential terms only from the voltage and current, and we find the sparse vector of coefficient. And since in the enhanced SPM, we have the value of the V, but we don't have the value of the V dot, we will find the V dot by using the first degree of finite difference method, and TS is the sampling time. So for the model 1, the optimal parameters are found through an exhaustive grid search approach. A set of 25 evenly spaced values between 10 to the power of -5 and 10 on a logarithmic scale are tested. And for both of the ST ridge and ST lasso, the value of lambda would be equal to 10 to the power of -5. And for the ST ridge, the value of tolerance is 1.78 times 10 to the power of -2. And for ST lasso, the value of tolerance is 1.78 times 10 to the -4. So as we can see here, the ST ridge has a larger tolerance, which means that it gives us the more sparse data. Even as we mentioned before, ST ridge has a better result for the correlated data. And even here, the figure shows the AIC inspired loss function for the ST ridge model with the lambda to the power of 10 to the -5, and it demonstrated that the very small value for tolerance results in the non-sparse model that overfits the data. For this, we pick the largest value of tolerance with the smallest value of loss function. So after finding a value of the lambda and tolerance for model 1, we are going to identify the batteries. So the measurable data for this model is the current and voltage. And here we pick the input as a random signal with amplitude equals to 5 ampere and sampling time. Here is 1 millisecond. And then we use the 500 data or half of the second data for training and 1.5 of the second or 1500 data for validation, and the normalized root mean square error for validation is 1.21%. And the data found from the ST ridge method. However, for this data, we find the coefficient for both of the ST lasso and ST ridge to show the difference. And as you can see, the additional terms appear in the ST lasso. That these numbers are the coefficient, and the library terms, they are theta. And since we have more additional terms in the lasso, since the tolerance of the lasso is smaller than the ST ridge, and it shows the ST ridge gives us the more sparse data. So for checking a generalization of model 1, the identified coefficient from the random input simulation is used. So we use the coefficient from the previous slide, and then sine sweep signal input is implemented to evaluate models 1 applicability to other type of input. And as you can see, the input is a sine sweep from 1 Hz to 100 Hz, and the normalized root mean square error for the system is 1.59%, which shows that the system is generalized also. And also for checking the robustness of model 1, we use the noise signal with the mean magnitude equals to 15% of the variance of the data set. And we use again half of the second for training part and 1.5 of the second for validation. And the normalized root mean square error for validation is 1.97%, and it shows that the system are robust to the noise also. Now here for varying SOC, here we use the model 1 for the different range of SOC, which means that for each value of the SOC, we use the model 1 and find the one value of the KC, and we notice that the parameters vary with SOCs, but the parameters has a smooth trend, so you can use a multiple set of parameters, and it requires switching parameters for each value of the SOC. And here is the trend of the parameters for the whole range of the SOC for the model 1. And here in the test that we have done so far, we use the SOC equals to 38%, and these are the parameters from the random input that we found in the past. And here are the parameters that shows for the cases theory, which is correspond to the V square, the value is 293, which is shown in the figure also. And for cases 7, which is corresponding to the sign of V, the value is 252. And for case 9, which is corresponding to the I, the value is -8, which is shown in the figure. And for case 14, which is corresponding to sign of I, the value is almost 0. So here we can augment model 1 with SOC and make model 2. So in the model 2, we dot with the function of the voltage, current, and SOC. So for model 2 in our library or our data, we make the function of the voltage, current, and SOC. But in the model 1, we only have a function of the voltage and current. So if we use the model 2, then for varying SOC, then we only have a single model, then there is no need for the switching or interpolation at each different SOC range. And in order to check the performance, we use the US06 driving schedule. Here it shows the velocity profile of that, and we use the current corresponding to this velocity profile. So by using the current corresponding to this velocity profile in our enhanced SPME, we got the following SOC and voltage, and as you can see, the SOC varies from the 40% to 25%. And then for finding the optimal parameter, the lambda was 10 to the power of -5. And again, here the tolerance of the ST rate is larger than the tolerance of ST lasso, which means that it gives us the more sparse data. And for identifying the system of the US06, we can see that the normalized root mean square error for validation part is equal to 4.78%. For the model 2 for the varying SOC of US06. So here we propose the data-driven models using input-output data, and then performance of the model was assessed via validation and generalization test. And model is robust to the noise, and by incorporating SOC in the model, we can track the battery's output during charge or discharge. And in the future work, we have planned to extending the method to accommodate aggressive electrical current input and implement a controller for the fast charging. Thank you for your attention.